Hello, my dear student. Today I am going to explain one topic selected from our chemistry portion. The topic selected is the valence bond theory and its approach to bonding in coordination compound. Just before to the point of the theory, we have to remember the scientists who already contributed their knowledge to develop the theory. Initially, in the year 1902, G.N. Lewis gave the idea about the electron pair sharing to form chemical bond. And then in the 1927, two scientists, that is Hitler and London, gave some modification about the pairing of electron to the covalent coordinate character. Finally, in the year 1931, Louis Pauling used the atomic orbital to give proper geometry after the hybridization of the atomic orbital. Now let us know what is complex. It is the combination of Lewis acid and Lewis base. The Lewis acid part have the capacity to accept the lone pair or the electron pair donated by the Lewis basic part. In the complex, the acid part represented by the central metal ion, also represented by a letter capital M, and the basic part, that is having the capacity to donate the bonding pair, that is electron pair, to make the coordinate bond between the acid part and the basic part, is represented by L, that is known as ligand. That means having the capacity to donate the electron pair between the metal and ligand to make or to result as a coordination compound or complexes. In the complex, it is represented within the square bracket. That is the acid part, that is we know the acid part is central metal atom, and the basic part we represent by L. Within the square bracket, both the L and the M are kept inside the square bracket, and it may carry charge. It may be in the form of positive, or it may not carry neutral, that is no charge, depending on the partner ligand. So here some important terms to be understood about this coordination compound. Here the part we have to understand is number one, oxidation state or oxidation number of the central atom, and number two, that is the coordination number, that is the number of ligand around the central atom coordinated by the ligand, that is the formation of the coordinate bond between the ligand L and the M. So this part, that is the number of ligand and the central atom, are known as the coordination sphere. The sphere may be charged or neutral depending on the nature of the ligand. Let us try to understand the main postulate of the valence bond theory. That is the number one postulate. Central metal or central metal ion provide suitable number of or vacant orbital, that is suitable number of vacant or empty orbital to achieve the electron pair from the donor ligand. And number two, the vacant orbital of C.M.I hybridise to give a hybrid orbital for the proper geometry with the ligand. Then number three, the hybridized orbital of the central metal atom overlap with the atomic orbital of the donor ligand having the sigma electron to form the coordinate bond. That is, to form the coordinate covalent, means covalent coordinate bond. And the point number 4, the hybridized part of the central atom may be from the n-1 d orbital or n-d orbital, depending on the strength of the ligand. In the last, that is the 5th part of the postulate, that is the rearrangement of the unused or non-bonding electron, that is mainly unpaired electron of the central atom, may be in the form of pair or may not be pair. That is, pairing or unpairing depend on the strength of the ligand. If the strength of the ligand is strong, that is, it forces to pair the unpaired electron of the central atom. Or if the ligand is weak, it is never forced to pair the electron of the central atom. These are the 5 postulates of the valence bond theory. Now let us come to the example using the theory. Now we have to proceed the explanation part, taking related example already asked in the previous year. The examples, from the example we can learn different type of ligand and some term present in the coordination complex, that is coordination compound. Let us take the 4 example. Now the first example is known as hexacyano iron 2, and the second example is hexacyano iron 3, and the third example is tetracarbonyl nickel, and the fourth example is tetrachloronickel 2. These are the examples. There are so many examples we can learn after getting the full understanding about the theory. Now come to the example. Here in the first example, that is hexacyanoferrate 2. In this part, iron and the cyanide, that is Cn, the number of Cn represent the ligand, that is the donor that make the coordinate bond between the iron and ligand Cn. The oxidation state of the iron is 2. It represented by the Roman figure. It shows the loss of 2 electrons. This is the central metal atom. This is iron 2. It shows the electronic configuration like this. That is argon 3d6, 4s0 and 4p0. After losing the 2 electrons from the 4s, it comes like this. Then the orbital figure we can draw like this. This is the orbital, this is 3d. This 3d is represented by this sub 5 orbital, and this one represent the 4s, and this one represent the 4p. This is 3d, 4s, 4p. So the ligand, that is the partner ligand, is strong field. Strong means having the good donor. Means I have mentioned the ligand, that is there are 3 types of ligand I have shown in the figure. That is and one is strong ligand, good donor, always act, means always try to force the unpaired electron of the central atom, that is to force to pair the unpaired electron of the central atom. And whereas average ligand do not force, that is sometimes it act as weak or strong depending on the condition. But in the weak ligand, it never forced to pair the unpaired electron of the central atom. Then you can see from the electrochemical series I have mentioned in the lecture. Now come to this. This ligand is strong field ligand. It forced to pair the unpaired electron of the C.M.I. Here unpaired, how many unpaired electron present? 1, 2, 3, 4. So these 4 unpaired electron pair up like this. There is no change, means there is no increase or decrease in the electron of the central atom represented by the blue mark. And these are the pair, these are the unpaired. Why these come to this pair? Due to the strong field of ligand. And the ligand, that is Cn, try to donate the electron to make the coordinate bond like this. This is red mark, this is The pair of electron represented by the red mark is the electron from the donor ligand. Here the 6 ligand donate the 6 pair of electron to the central atom like this. The orbital, that is the central atom orbital of the central atom, that is 1, 2, 3, 4, 5, 6. These orbital we cluster like this D2sp3. Then means these are the hybrid orbital, that is they combine to give a single one known as D2sp3 hybrid orbital. That is this orbital give the geometry, this is octahedral. Come to this octahedral figure. This is the iron central atom present here, and this represent in the coordinate bond formed by the Cn, formed between the Cn and the central atom ligand. There are how many coordinate bonds? 6 ligand due to the presence of the 6 ligand. That is 6. This 6 also represent the coordination pair, a coordination number. That is the number of the ligand around the central atom. So this is the figure shown in the 2 dimension, but in the 3 dimension we have 6 corner. That is 4 corner in the plane, and above and below the plane 1 corner each. So to tell you, in the 3 dimension, this is known as octahedral figure having the 6 corner. From the 6 corner, in the 6 corner, the 6 ligand present and coordinate to the central atom. It carries the negative charge like this. Here, this is the negative charge of the complex. That is coordination part of this complex. Example 1. Come to the second example. That is the same example that is here also hexacyano iron 3. Only thing, the first example and this example slightly different due to the charge of the central atom iron. In the first example, iron carry the positive 2. In this second example, iron carry the positive 3. That means iron lost 3 electron in this compound. That is, after losing the 3 electron, it show the oxidation state plus 3. Come to the electronic configuration as given in the figure, the 3D. In the first example, 3D is 6. In the second example, 3D is 5. Here the 5 electron in the 5 orbital I have shown in the figure, orbital figure by blue mark. That is blue signal, that is blue arrow, represent the electron of the central metal ion, that is iron. In this case, here also the ligand is also strong ligand. This is, it has the powerful electron donating capacity, and it always try to force the unpaired electron of the central atom. So like this, after pairing we have the electron, that is 3D electron come like this. That is, there are 2 pair and 1 unpaired electron, and the remaining orbital, why the remaining orbital left? To get the electron pair from the ligand Cn. The donor ligand donate the electron pair to the central atom iron to make the coordinate bond like that, the first example that I have shown. Here also the same geometry and the same condition, but only thing the number of electron is different. Here the unpaired electron, 1 unpaired electron present. In the first example, no unpaired electron present. Due to this, the properties of the complex is different. This is very important. Come to this. In this case, the red, that is the red mark represent the electron pair from the Cn ligand. It make the 6 coordinate bond to the iron. It come, the geometry is octahedral, as I have shown in the figure, the octahedral geometry. Here it carry the negative charge 3 O as a whole. In this compound we can see from the properties of the valence bond theory. There are main properties, 4 main properties of the valence bond theory to write after this. The first properties is hybridization. How the geometry exists means the geometry of the compound under study will be in the 3 dimension. This keep by the hybridization. What type of hybridization it show? That means here it show D2sp3 hybridized orbital means D2sp3 hybridization resulting the octahedral geometry. Here then the second properties is magnetic moment denoted by the mu. I have given in the figure mu, that is the relation of the mu is given by the relation that is underscore, that is n, inside the n plus 2. It gives the magnetic moment. Here the n represents the number of unpaired electron. If there is no unpaired electron, it shows the magnetic moment 0. But here one unpaired electron present, so it gives non-zero value. The magnetic moment of the compound is non-zero. This is mu is not equal to 0. It will come root over 3 after the calculation using the formula I have given. In the third, that is third properties is what? Spin multiplicity. The relation of the spin multiplicity is 2s plus 1. I repeat, 2s plus 1. Here s represents the total quantum number. That is, how can we calculate the s? We can see, that is, we can observe the number of unpaired electron present. That means if the number of unpaired electron is 1, then the value of is half. That means it may be clockwise or anti-clockwise. If the electron is unpaired, the spin of the electron may be clockwise or anti-clockwise. Any one we can select. It shows the value is half. When the unpaired electron is 2, we can calculate the s like this. Half plus half, we will get 1. If the unpaired electron is 3, we can calculate half plus half plus half. That is 3 times of half. We will get 1.5 or 1.5. Like this, we can calculate the s value. Then, for this particular example, that is, we have the 1 unpaired electron. So, we can apply this number in the spin multiplicity 2s plus 1. That is, 2 into half plus 1, we will get the 2. The value of the spin multiplicity is 2. Then come to the last properties, that is magnetic character or magnetic behavior of the compound. This character generally reflects diamagnetic or paramagnetic. If there is no unpaired electron, that is, all the electrons are pure, the compound is diamagnetic. All the diamagnetic compounds are colorless. Then, if the number of unpaired electrons present, it may be 1 or 2 or 3, any number, but the presence of unpaired electron show the paramagnetic. That is, all the paramagnetic compound is color. That is, to show the reflection, that is, within the vibgyor region. Like this, we can proceed in the third example. Let us practice the 2 remaining example, number 3 and the number 4 simultaneously, because we have some knowledge from the first one and the second one example, so we can apply the knowledge here directly. In this complex, that is the third complex, carry the negative, that is the neutral charge, that is the neutral complex, and the fourth one is the charge carrying complex, that is anionic complex. But the central atom or central ion is same, just like the first example and the second example. Here the central atom show the plus 0 oxidation state, and this one show the plus 2 oxidation state. Means it does not lose electron. But here the right example, that is in the fourth example, it show the loss of 2 electron. After losing the 2 electron, it show the electronic configuration like this. And here the electronic configuration is given like this. So all these electron and all these electron have different environment. Here the same electron present, here the 2 electron loss due to the plus 2 oxidation state. Here only thing, the ligand is CO, which is strong ligand. From the electrochemical series, this one also strong field ligand, and this one is weak field ligand. That is the poor capacity of electron donating. It never force the unpaired electron to pair. But the strong ligand always forced to pair the electron of the central atom like this. The electron get pair, that is the electron goes to pair in the 3D orbital. here as usual, it does not force the electron to pair, so it remains like this. But here this cross mark, I have shown the cross mark represent the electron pair donated by the ligand CO. In the right one, here also the cross mark represent the electron pair donated by the ligand Cn, that is chloride, means we can call the chloro. So this geometry, after the hybridization, we have the geometry that is tetrahedral. This is the geometry that is tetrahedral. We have tetrahedral geometry bonded. Here also tetrahedral geometry. Only thing we try to know the properties of the valence bond theory by applying this thing. This is the geometry. Number one properties is hybridization. Here hybridization is sp3. Here also hybridization is sp3. That is same geometry. And the magnetic moment, that is given by this formula. So here the magnetic moment is 0 because there is no unpaired electron, but in this case, due to the presence of two unpaired electrons, it shows the magnetic moment root over I Bohr magneton. In the spin multiplicity, here is 1 and the spin multiplicity is 3. So this one, another for properties is diamagnetic. This compound belongs to the diamagnetic compound and this compound belongs to the paramagnetic compound because its presence, the presence of unpaired electron, we have seen the presence of unpaired electron, so the paramagnetic and no unpaired electron is diamagnetic. Okay, I want to give this information that we have learned some idea applying the valence bond theory to the 4 example, that is 4 related example. In the first example, we have the geometry octahedral. In the second also, the geometry is octahedral, and there are different magnetic moment due to the different electronic environment between the first one and the second one, and the same, the magnetic properties also different in the first one due to the presence of no unpaired electron, that is all the electron are paired, it shows the diamagnetic. In the second example, the presence of unpaired electron show the paramagnetic. Now in the third and the fourth example also, one, that is the third example, show diamagnetic, and fourth example is paramagnetic. So I think you have learned some idea from this part. If you have any difficulty to understand, you can contact to our college link channel for your better understanding. Thank you, my dear student.